Well, so just put on the board what we, just to remember where we were. K is an integer at least 2. You are interested in k's power. We take sum of s powers. S will be here larger. It can be anything, but any integer, but we'll get something if s is larger than 2 to the k minus 1 plus 1, and then we'll try to see whether we can improve of that. N is a large integer, and so the representation as this is the in some way the Hardy-Ramanujan version in a truncated form, and since it is truncated, you can just integrate over the unit circle. And instead of z, you write e over n alpha, and you are just interested in the angle and not in all the complex number. Okay, so the x will denote n to 1 over k, and this is a sequence, the sum of length x. And the number of representation, we expect to show that it is something like this expression. Remember, we discussed indeed what it was about. This is just the average, because if you are looking at what is the average of alpha s of n, this is easy to compute. It's easy to compute that that its order of magnitude is this one. And if you want to have something which is a bit more precise, instead of counting stupidly into 2 cubes of different size, you take into account the real shape of the volume of interest, and this is responsible for the gamma factor. And there is also some arithmetic thing that the powers are unevenly distributed in the arithmetic progression. I don't say badly distributed, it's unevenly distributed. So this sigma will oscillate with the value of n, but in any case, as soon as s is larger than 4n, it will be always between 2 positive constants. So it's not so bad. So what we were looking at was, in some way, if we are close to 0, you remember we said if we are close to 0, then in this sum there is no cancellation. All the elements are just equal to 1. And this is also close to 1. And so this integral is at the length of the interval. And it turns out that the length of the interval you can take is something like 1 over n. If you don't want to have oscillation, because this is n, if alpha is 1 over n, this is just fixed and it's close to 0. The argument is close to 0 and the value is close to 1. So already you get something which is n 1 over k, which is the size of this, and you are integrating on an interval of length n, and so this is responsible for the -1. And so you have something which tells you if you are close to 0 or 1, then you have something which is a little proportion. At least it is of the same order of magnitude already. And the same thing if you are looking at quarter-half and something like that at around on the circle. I mean, I still see the circle as the unit circle. In this circle, if you are close to a rational with small denominator, it would be the same phenomenon, and you will get another contribution, and you expect all this contribution to collect in this. So on the arithmetic, I have not been precise. It's a bit of a mess, but if you know that it works and how it works, you have seen several times, by the way, written something like alpha plus theta, if it is A over Q, is something where you can factor out the elements which are of your Q, and one of the ingredients will be the sum of E of alpha N over Q, or alpha A over Q, and when N is mod Q. Okay? Those sums will enter the business N to the K. Times something which is smooth and which is similar to what was the initial sums. Okay? So you have seen, now you're more familiar because you have seen many people giving similar expressions. So the question is, well, you know now that if you are close to rational integer with small denominator, then you will get a good contribution. You will get this already for the contribution of sets which are around A over Q with Q small, and which are the major arcs. Now the question is, okay, you are talking about major arcs, how do you define them? We know that all the time it is to define major arcs is to say it is something like alpha minus A over Q is less than something. You remember there was something that was given, for example, in Agarwal, I think he was taking something which was B3 to, and then above there was some B delta. There was some tiny bit. So you have several ways indeed to define. You have a large flexibility for defining major arcs. Essentially, you can take for major arc anything which permits you to get back to this. And since it is just an equivalent you are looking for, okay, if you can win something which is power, you are happy. But for this, you have really a large margin. So this will be a trade between this part, and I didn't speak yet about the other part, which is what can you do for the other values for which you don't have, because they are close to a rational with a very large denominator, so this will not work. If you take something where you have too many, your arithmetic progression is very, very large compared to X, you cannot expect to say anything here. Okay? So there will be a trade between what we can do for the small part, and in this trade, you have a large margin. So large that in some way, if you want to do something numerical, or if you want even to get the good exponent, it may be a bit messy to know what to do, because you have a very large choice in which you can manage to get this type of expression. Optimizing is somewhat complicated, but it's not. So I think we have everything. So now I have to define what is my major arc. So as you know, maybe, I don't know if Dirichlet theorem has been mentioned. And recall Dirichlet theorem. Dirichlet theorem tells you the following, that, what is it? You take, let Q be larger than 1, then for every alpha in 0, 1, there exists AQ with 0 less than A less than Q less than Q, and AQ is our coprime, such that alpha minus A over Q is at most 1 over little q, capital Q. Okay? So the proof is a nice proof. It is the pigeonhole principle. Essentially, you have to be a bit careful on the edges, but you divide the interval 0, 1 into Q boxes of length 1 over Q, and the number of terms you have here will be something which is more than you take your set of A over Q, and you put them you put alpha in those boxes, and alpha has to belong to one of the box, or 2 alpha, because they are too numerous. You have more than Q plus 1. Not exactly, you have exactly Q of them, but you can manage with the edges. If one is in, you are happy. In the other edge, it's fine. And then you have only Q minus 1 edges and Q elements. And so 2 are in. And so the difference is short. And the difference, Q alpha, Q1 alpha minus Q2 alpha will be just another Q alpha with a Q different from 0. So, okay, so this is fine. And also, of course, this implies also, since Q is less than Q, that alpha minus A over Q is less than 1 over Q squared. This will be used in the sequence. This is why I wanted to mention that. So, okay, so the fine is to define the point now is to define our major arcs. So we let major arcs be of the following things. This is complicated because it is some Gothic M, but you have to use the large one and the small one. And they really look like the same. So you have to see both at the same time to know which one is the large one and which one is the small one. So M of AQ. Now I'm defining the major arcs for my problem, how they are defined. So, okay. So this is the set of alpha such that alpha minus A over Q, always when we're speaking about A and Q are coprime. If I forgot to say it, you just add it by yourself. Is less than, you know, it is the same construction as we're done. What we're going to use it, for example, here, is just to say, okay, you remember if it is something like 1 over n, it's just a bit too small. You have a large contribution, but there will be also some other point with large contribution around. So you have to extend it a bit. And then it will be some, remember I was saying it will be oscillating values. And so in some way, as soon as you tend to infinity, you're happy you will capture everything. What is remaining will be an error term. Except that if you are not taking too much care, you don't get the n. Yeah? So if you want to have a saving of a power, you better here go sufficiently large, so that the error term in this term, in this contribution of the major arc, will be with a good error term. And just I keep the notation delta of Agarwal. And for example, delta here will be 1 over 100. You remember we were saying something like 5 delta has to be less than 1 or something like that in this talk. Okay. So now one point is to say also what is Q. Okay. So the point is that what you want when you are doing this, you are going to say that the integral is first the sum of the integral over the major arcs. So what you need for that is to say that there shouldn't be overlap between the intervals. This is very important because otherwise in the integral, you are adding twice something. This is not good. So one point which is important is no overlap. And another thing, of course, is that you should be able to say that there should be enough so that large enough so that sum over M, that is to say, let us have the union of the MAK of interest. So I'm going now to bound to say major arc. That is to say you have 0 less than A, less than Q, less than something, always AQ is equal to 1. And what you want is that the union of S alpha to the S e to the minus alpha n, this is equal to ZUP, this term. 1 plus theta rho of 1 delta and so on times this one, and you expect that the other part will be just a big O of n delta n to the S over k minus 1. At that level, you don't need for the error term to keep anything like that. Just big O of n plus big O of 1 minus delta this time will be fine. So this is what you expect. And of course, there is a third constraint that you are able to say something on the complementary part of the major arcs. But we don't know yet what to do, so let us keep it like that. So this is not finished, because I have also to say, I am able to say something on the other part. Okay? So this is not the end for the major arc, but I will come back and tell you how to define the major arcs. But before that, I tell you how we do with the minor arcs. So what we call minor arcs, I hope you see it is M. This is 0, 1 minus what is capital M, which is the union. Capital M, which is the union of the major arcs. So which are called either major arcs or major arc. It depends if for you an arc has to be something connected, then the minor arc is not connected. So people say minor arcs. Okay. So now what are you doing here? So if you are clever for the minor arc, of course, you think of Dirichlet, you can always approximate something like that. And in some way, you are saying, if I have an approximation with Q, which is small, I am happy. If I have an approximation with Q, which is large, this will be the minor arc. So in any case, we're expecting that some element in the minor arcs have some good representation, some good approximation, let us say, of this kind. And this will be enough with Q sufficiently large. So what we would like to have, and I'm now going to define precisely where I stop. Minor arcs will be the following. This I go here up to x to the delta. Okay. Now the point is that if I do that, you are better to go back to Dirichlet and to say, okay, if you have something with a small approximation, then you will put it here. But what I want to define as little m is the following, and you have to think a bit of the following. There exists the set of alpha. Zero, 1, such that there exists AQ. AQ is equal to 1. And XS less than Q less than X to K minus delta. K minus delta. Okay. So what you have to check, and the set of alpha for which there exists a Q such that alpha minus A over Q is less than 1 over Q squared. This is not true what I am saying, but what I define is that I take M, this is the definition, and this is a property that M is included in this set. That is to say that what I say is that I have the good guys. This is A over Q, with Q which is somewhat small, and I have an interval here. What I don't rule out is the possibility that here there exists a minor arc, not a minor arc, but there exists an A over Q with Q large, Q larger than X delta N over N minus delta. Is it? No. Yeah, it is better to put it in X because otherwise you have to divide by delta. And larger than X to 1 minus delta. No. Larger than X. Is it what I want? No, X delta. It is X delta. Sorry, now you don't read anything because if I read that. So this is larger than X delta. And what I am defining with A over Q up to 1 over Q squared, maybe large, and maybe this. So what I say that the set here is a set so this set, you have to check, this is easy to check that. But be careful, don't start with this. If you want to say that this set is included in M, this is not true. What you have to say that if you are not in this set, then of course, Dirichlet will tell you there exists a Q such that and so on. And so it will cover this.
I think there's a capital Q is N upon X to delta.
Yeah, so of course. So all the number I'm going to consider are this.
Delta.
Sorry? Yes, yes, delta looks like an S, yeah. Sorry. So I take all the powers up to X to delta, and with that I can cover everything. This is fine with 1 over Q to the delta. I forget even the Q here. So this will give me the Dirichlet business. The one with the small character, this is my major arc. What is my minor arc is the complement. And what I can show is that if I am in the complement, there exists an approximation, a good approximation with Q, which is larger than X delta. Okay? Now, this has no importance here that there is overlap, because what I am going to do is just to give single upper bound for a sum in the minor arcs. So it may well be that this part is treated in this major arc. Well, what I am proving is that for this one, there will be also another part, an upper bound saying it is small. Well, this is not a problem. I don't care. So what is important is to be sure that this set and the minor arcs have a union which is 0, 1. And then in this part, I select what I want. Okay? So for me, when I am taking an element in a minor arc, I am just going to give an upper bound for all the elements which are here. I don't care whether in the minor arcs or not. I give an upper bound. So this is the question of minor arcs. Possibly, if I were keeping the numbering, I would be in 5, which is minor arcs. And so now everything is fine, and I know that all the Q I will have to do to study are Q, which is up to K minus delta. Yeah? So for that, there is something that has been stated and used, if I'm correct, at least twice already. And so I just state it again, and I will wave hand to tell you how it goes. Welles inequality. You know, in 1916, Hermann Weyl was studying uniform distribution mode 1. He introduced that, and for that, he was considering several sums. And so one of the questions was to know, for example, whether the sequence, if alpha is irrational, whether the sequence alpha n to the k is uniformly distributed mode 1. And for that, he had to find some upper bound for this, to show that this is, you have an upper bound. This is why you have the name of Weyl. And if you think in the history of the business, 1916 is just a bit after Hardy and Ramanujan. I think it was 14, no, or maybe 18 even, maybe 18. So it was about the same time. And when Hardy and Littlewood started also to study went on studying for the powers, you had also this. So it is at the same time. You see, all these things were in the air at that time. So Welles inequality was just to say, yes, there is an upper bound, and is upper bound is nice. I will tell you how you get it. So let AQ is equal to 1. What is interesting that you are not interested in the size of Q for the time being. Any Q is good. It works with this with this inequality. And this is why it was enough. We do that because of this. And if you have some function, even if it's for a polynomial, it did that. And even better, but you don't care at all about the other coefficient. They will not have any importance plus alpha 0. And you take T of phi, which is just the sum, you know, which is sum from n is equal to 1 to x. In some way, x is a free parameter now, but E of phi of n. And then what you get is the following, that maybe, I don't know if I have to use it later on. I will say that T of phi is less than x to the 1 plus epsilon. So this is, x is the trivial upper bound. You have x term with modulus 1 in your sum. Epsilon is something you are losing because there will be some divisor function. There will be a few things like that. And then you try to see what is the saving. Saving is indeed 1 over q. So if q is too small, don't expect anything. But we're going to use it when q is already a power of x. So it's fine. There will be some saving. Then you have, in some way, some trivial term. Usually you don't see it, but if it turns out that you have some curious values, you better keep it. It's just for safety you keep that, but this is always good. And then you have something which is q divided by x to the k. So again, it tells you, haha, q has to stop somewhere, has to be less than x to the k. And if you want some polynomial saving, you better take q between 1 power of x and something which is a saving with respect to x to the k. And you see, it's fine, we're on the good shape. Q is larger than a power and smaller than a power. And this is not like that. This is to a very small power. This is to power 1 over 2 to the k minus 1. K minus 1. Here. If you forget about the k, think it is 1 over 2 to the k. So saving is not that great. Good. So proof, sorry? Phi of n. Ah, yes, it's phi of x. Yes. Thank you. Yeah, thank you. Okay. So this has no importance. Indeed, what you are doing is, well, if you are a polynomial of degree 1, then situation is fine. For degree 1, what you get is just a geometric series. You have geometric series, and sum of geometric series is quite easy, and you get something which will be something like E of for the sum of the series, alpha n plus 1 minus E of alpha divided by 1 minus E of alpha. Okay? So this is fine. So the numerator, you have no difficulty. This is at most 2. And this is essentially the distance of alpha to the nearest integer. Maybe there is a factor of 2 that cancel out with the other one, but in any case, it is the order of magnitude. Okay? So now, of course, when you are saying this is the size, you have to take care, well, be careful if alpha is really too small, then better use the trivial estimate and to say that this is at most x. So in degree 1, the upper bound will be the minimum of x and 1 over distance of alpha to the nearest integer. Okay? You have seen this several times. And now what you do is you are differentiating. When you differentiate, you are lowering the degree. So what you do, you take, for example, first k is equal to 2, then you are squaring S alpha, and you have something which will be alpha n2 minus m2. And n2 minus m2, you just write it as a product n minus m times n plus m, for example, and you change variable. So you are always summing on intervals which have a length which is about x, 2 times. And on the one sum, it will give you something which is the minimum of the length you have, which is x, and something which is 1 of x to alpha k. And now you have to sum that on k. Okay? And, but you know now, that is interesting, that alpha is essentially a over k. Plus a little remainder, but essentially it will turn round. This is why it's good to have an approximation with k, because this will turn round. So this sum, when you are taking on one period in k, when it turns round k times, what you have, maybe you have 1 or 2 elements which are pretty small, but then you have something which would be 1 over k, 1 over 2k, you have just something which gives you a log. So finally, what you will get is an upper bound for 2, which is x times the log. I was at the level, I mean, k was not the right expression because k is already given a name. So it is something like h. There will be a factorial 2. Yeah, but okay. Let us say that this will be 2. I am just at the first, I am just doing it the first time. I'm just doing the first time. K is equal to 2. K is equal to 2 for the time being. So, okay, there will be a factor 2. But essentially, it is something which will be linear. Even if you have, in general, there will be, so for 2, this is what you get. And then you understand that if you differentiate again and again, then there will be something which is a factorial, and indeed you don't use the factorial at all. You replace the sum by the complete sum over the element, and this gives you a log, and you know that if you modify slightly a log, it has no importance. Okay. So this is, now we can start to give some first application. So Bayes inequality, it is written here. And what you know is that it tells you that if alpha, I don't know, if alpha belongs to M, then I have something which will tell me that there is some saving S of alpha is something which will be less than X, and there is a small saving which will be something like, so this is 1 plus epsilon minus X minus delta over 2 to the k. And if I want to get rid of the delta, instead of putting k minus 1, I put k. This will be enough. In any case, it is the order of magnitude. Fine. This is just veil business. And now you see what can you say out of that? This is the discussion we had about k2 to the k. So now you see if you take S, so you have the following. The integral on the minor arcs, on the major arcs, is something of this side. The integral of the minor arcs is something which is this time. So what you get is this, that the integral over the minor arcs of S of alpha to the S, let us say that S is not, for the time being, just 2 to the k plus 1 exactly, but something larger than 2 to the k plus 1. Okay? So we say that S is 2 to the k plus L. Oh, leave it like that, yeah, okay. For the, no, this has no interest. S is larger than k, 2k plus 1, and it's in now. So we have S, the alpha, is less than x to the S minus S delta over 2 to the k. So on the one hand, you have the contribution of the major arcs, which is something which is, I put it in x. You remember that n is x to 1 over k. So what you get is something which is S, this contribution, let us say, sum over m as the order. X to the S minus k. I replace n to the s over k minus 1 in terms of x. And x is s to 1 over k. So this is the n minus 1 that you had, and this is the n to the s over k. I put everything in terms of x so I can compare. So now you see this is x times a factor which is less than 1. And this is s minus something. So if s is sufficiently large, then this will be smaller than that. Okay? And you see it's not too difficult to say. If you say that if s minus k is larger than s to the 1 minus delta over 2 to the k, then our ks of n is positive or n large enough. Okay. So of course s disappears with this one. And so you have to have something which tell you that so it is s is larger than k 2 to the k over delta. Okay? This implies that you have this. So you see, it's nice. If you remember what was the Hilbert proof, Hilbert proof told you that S has to be at least k to the k to the k to get the solution to solve ring. So it tells you at the same time something more, and it even tells you more that you have an equivalent for the number of representations. Okay? So now we are not still completely happy because we know that little g of k is something like 2 to the k plus a little thing, 3 over 2 to the k. So it is essentially of the size 2 to the k. So even if you know that everything is explicit here, you can make explicit computation. There is no argument which would be non-effective in the proof, and you can compute everything. So you would like at least to go to something which is a bit smaller than that. And then I will give you a few tricks. One trick is to say, maybe we can drop the fact that we are looking for exactly all the representations. Maybe if we can find some nice representation for which we can prove that there are better representation because they are well shaped, then it's fine. And there is also, this is why I was mentioning Hua in 1948, because Hua was able to do a bit better than that. And the point is the following. Let us try how we can improve on that. So I think major arcs, I can drop Dirichlet and major arcs. So I am concentrating on the major arcs, on the minor arcs. The major arcs, we know how everything is going. And indeed, we can drop, it is not from here that the 2 to the k comes. We know that this is fine as soon as n is larger than 4n or something like that. There may be difficulty at the beginning with that, but if you are larger than 4k, I mean, then you are done. So there's no problem about the major arc. I'm not going to touch the major arcs and speak only about the minor arcs. So about the minor arcs, I'll tell you about Hua, and then, well, yeah, then we can stop for 5 minutes. But I'll finish with that, with this idea. So you are looking, for example, as S of alpha and I'm always on the minor arcs. So I'm taking something like that, S alpha, D alpha. Okay, then what I know is if I am using Weyl bound, that I have a saving, which is, so there will be something like x to the, what is it, 4? No. Okay. Let me say something maybe a bit better to be k plus, yeah, S. Okay. I have a saving, which is S times delta. Delta over 2 to the k. Fine. Yeah. Okay, so this is the saving. The saving is showing that. Now there is one way to get something which a better saving at almost no cost, which is to say that on average, on the minor arcs, usually this is the place where the value are not that small. We're taking with absolute value here. So really it is, don't expect any cancellation in the integral. You're integrating a positive function. So you are taking out, you're on the minor arcs, it should be small, but there is a way to say that on average it is small, just to use Parseval. You see, we are doing something, what we should be able to say is something about the S norm of S alpha. And we're giving some information which is much stronger because it is on the infinite norm. So now you have the possibility to say, okay, infinite norm means that I can take the maximum out of it. It is uniformly bounded here. I can take it out. Well, take it out like that and consider that it is the maximum over M of S times, and you take it a certain number of times, and then instead of integrating over M, since you know that it is small, coefficients are missing here. I can take something which is up to 0 and 1. But then I'm happy, I say, okay, if I keep a 2 here, and here, I will have something like S minus 2. Here I have a good saving because I have a saving of X. So I take 2S, and I have a saving of X. So in some way, for those two, instead of having a saving which is 2 times delta over 2 to the k, I have a saving which is 1. So it's great. Okay? Well, now you say this is very nice, so let us do it for 4. Okay, then you are going to solve to know the number of solution, the number of representation as an integer as a sum of 2 squares. But this number is something like a divisor function. If you think in Q of I, you will see that it is a divisor function, or instead of saying the sum of the 2 squares are equal, you just shift them and you say the difference between 2 squares are equal, and then it factorizes completely. So you may lose, you have a sequence on which you have just a divisor function, and if for this sequence you use Parseval, you will lose the square of it. This is again something x to epsilon. So if you use that, then you will get that this is big O of x to 2 minus plus epsilon. So if you use 4 of them, you still are winning something. Okay? And now what was noticed, but only later on, that you can go further that way. And this was proved by Hua, 1948. It proved the following, that for what L between 1 and 2 and K, then K is the exponent here, it is the power, it is the same one. Sum from 0 to 1 of S of alpha, well, but you have to do it a certain number of times. S to the 2 to the L, d alpha, is larger than, so it is some x 2 to the L, but your saving will be L plus a tiny epsilon. Okay? So now this is fine. It means that if you go up to k, if you are taking 2 to the k element, then you have the complete saving of x to the k. And this is fine because if you have now the complete saving of s to the k, then what you get always, this is always true, but then now your saving will be, you see, you have to gain back this k, and this what gives you that. So if you just take s2 to the s plus 1, then it's enough because you have a saving from Weil. If you take 2 to the n plus 1, you take 1 out, which will give a little saving, and this one will just compensate up to an exponent epsilon, but you have a positive saving in the constant. In some way, this is why you need always to have something to have a saving with the power, because you are always losing something like x to epsilon. Just one final word. This is by divisor function, and you are taking the maximum of a divisor function, and this is very bad. Maximum of a divisor function is a function which is, I mean, it can be very large, but on average, it's fine. And if you follow the proof of Hua, then you can replace that by averages of divisor function over polynomial values. But this is fine. You can also do with that. It is sufficiently regular. So you can replace that by something which is smaller. And if you are doing something effective, it's quite important. So, okay, we are going now to see what were the different, some tricks of Hardy and Littlewood, one trick, how it was developed by Davenport, and then outline some two application, Roth theorem, and also something else, but just more and more waving hands. Okay, thank you. So in 5 minutes, we can be back. What did I say? Yes, so we are on the side of having a little g of k, and this was done in the 30s, among other by Dixon and by Pillai. And then there were just a few values, and you know the history, and it's fine. Good. So now what I want to say is to do something to improve on the bounds. This is the last chapter in some way, or section in Waring. Improving on the bounds. And I have to introduce something which is what I call G of K. So you see, we were denoting little g of k, the least number, so that you can write every integer as the sum. But it turns out that this is only for rather large, rather small values you get example. And indeed, the worst was just try to look at all the integers up to 3 to the k, and then you will find the worst case. There might be a few other behind that, but essentially this is, for example, if you look at 9 cubes, 23, you will get 23. You will get also 239 somewhere. For some reason doesn't work. And then after this one, everything, and this is not, is sum of 8 cubes. And what we expect is that indeed, every integer, I think I mentioned that already, every sufficiently large integer is the sum of 4 cubes. So the most interesting value, maybe than the little g, which has historical interest, is the value to know what is the best you can do to represent all sufficiently large integers. And this number is called capital G. So of course, capital G is less than little g. I don't know if it is the reason of the notation, but something like that. So what we expect, for example, just to expect little g of 3 is equal to 4. Known little g of 3, this is due to Linux, is at most 7. So there is some gap. It is better than 9, which is little g of 3, which is equal to 9. Not much is known, although all the value of little g of k are known, almost no value of little g of capital G are known. I think the only known value are g of 2, which is equal to 4. This is fine. Everybody is a sum of 4 cubes, but if you take someone which is congruent to 7 mod 8, it cannot be represented as a sum of 4 squares. So done, you have g of 2 is equal to 4. And the only one, the next one to be known is g of 16, g of 4, which is equal to 16. Although the little g is 19, you need 19 biquadrates, but with 16 biquadrates, it's enough to represent everybody. Okay. So in some way, we need now to do even better than Hua if we want to go there, because Hua will block you. You have to take at least 2 to the k element to do something. Okay. So there was a trick which is the following. I will formulate it like that. Let W be a set in integers, of course, in 1n. By that I mean all the integers between 1 and n. All terms of which are sums of, I don't know, let us say, t kth powers. Okay? And you know something about W. W is rather large. Let us say W is Wn, it is in n, is n to the, I don't know, 0.9. Compare that. Assume you have something like this. I didn't mention, but of course, very close to Waring's problem is the question of Goldbach problem. Goldbach problem is the same with primes. Can we represent every sufficiently large number? If you say a sum of 2 primes, then circle method gives you nothing. You see, at some point you have to use minor arcs, and you cannot say anything with 2 elements. You cannot even use a Parseval. Parseval would define gives you almost everything, but a tiny bit is still needing, and you cannot do that. But you know, for example, that the sum of 2 squares, 2 primes, have at least a positive density. This can be done with elementary mean. Indeed, it has asymptotic density 1. This is known also. And yeah, I'm already thinking that primes are all odd, and sum of 2 primes are all even. You are right. Yes, thank you. Okay, so the same way we are building things, and you can see how we can manage to produce sequences like that. Now, what is interesting is that if you want to represent an integer, we call it capital M, let us say around the size of n, because or less than n, then what you can do is to represent an integer m as a sum of 2t plus r kth power you can try to represent it m is equal to W1 plus W2 plus N1k plus blah, 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 plus nrk. So you are taking 2 elements from W, and you are taking this number of elements. Yeah. And so you go into circle method, you know everything. So what you will have is a representation of the number R of M. Yeah, my notation, one was false. By the way, when I wrote it, this is gamma of 1 plus 1 over k to the s, thanks to someone who showed it to me during the break. And usually I was using RK instead of RKS. So this is just to be consistent with my notation. R of M, well, you know what it is. It is summation from 0 to 1. And then you have something which will be a T of alpha square. And then you will be your S of alpha. S of alpha is what you think it is, 2 power R, the alpha. Okay? And T alpha, what you expect, is the sum of when W belongs to N, belongs to capital when L B belongs to W. No, W is fine. Little w becomes to the number of S of alpha. S alpha, E of alpha W. Yes, yes, sir. Is it M I want to represent? And then be used as being the size of the thing I'm looking for. Okay. So, or I can put N also, not a problem. Fine. So for the major arcs, well, a priori, you would say there is a problem because I don't know at all what is the structure of this set. But you know pretty well how this one is organized. And so you just say, okay, I am splitting here the sum, and I'm taking 1W for 1W given. I know pretty well how things are organized in arithmetic progression because I know how it is for the element in this sum. Okay? So for the major arcs, essentially this depends on this. This is not much important. What about the minor arcs? And this is on the minor arcs that you are winning a lot. Because on the minor arcs, what you are going to do is to say that the integral of the minor arcs of T of alpha squared, S of alpha to R, modulus of E of minus alpha n, which is not here. And of course, what you do is this. You take the maximum out, and the maximum, you know how it is. It will give you something which is x being the n to 1 over k as usual. You will get something which is x to r minus r, your famous saving, let us call it little delta, capital delta over 2 to the k, or something like that. You have a small saving here. And the saving here is gorgeous because for this one, you just use Parseval. Okay, and then you get something which is x to r minus r delta, and then you get something, at least it is less than. And then you get something which will be n to the 4.9. Okay. Whereas in the main term, what you expect is, as usual, what you expect here, Rn is expected. And when I say expected, it means also this is the contribution of the major arcs. Major arcs, everything is as you expect. Rn is expected to be what? Well, you have n to 1.8 And then you have something which is plus R R over K minus 1. Sorry? On the major arc, I get 0.9, which is a bit larger than 0.8, but not much. You see, instead of having something which was like S or something like T, there would have been a factor T here. There is no T, it is something very small. So you just need, with this delta, to get rid. So you have the R over K, this is, and this is N. You can put everything in terms of R. This is N to R over K minus R delta over K and so on. So you have almost recovered everything. The R over K is this one. This is fine. And here you have something which is 0.8. And so the closer you are to 1, the best you are, the less you have to save. If you have already a set of density 1 or almost 1, then you just need a tiny bit and you are done. Okay? So this was used in different ways, but essentially it was introduced by Hardy and Littlewood, and then it has been much developed by Davenport by looking at this type of thing. What Hardy and Littlewood were doing, yeah, I have just a few minutes to say that. What Hardy and Littlewood are doing, maybe I keep that because this is, okay, this, I don't care. Okay, what is the construction of Hardy and Littlewood? I lost page 4. Construction of W. So you take Z, large integer. You see how to connect it with N, and then, but with K, I tell you how it is. So you define successively Z1 is equal to Z over 6, and then by induction, Zj plus 1 is Zj to power 1 minus 1 over K for J up to T if you want. Okay? And then what you are looking at is you are looking at the representation, let us say W, is a set of numbers which has N1K plus blah, 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 plus NTK, with the following that Nj belongs to Zj plus 1. No, 2Zj. This would be too large. Of course, you lose everything if you're doing that. Okay. Now, if you think a bit of that, you will notice that if you take an element in W, it has a unique representation as something like that. So this is definitely a construction of a set W, which can be larger, rather large. You can check what it is, that you don't lose too much in it, which can be rather large, which you have this. Okay. Well, let us assume that N1K plus blah, 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 plus NTK is equal, with the Ni prescribed in the subinterval, is equal to M1K plus blah, 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 plus NT to the K in the prescribed interval. then you have the following, that N1K minus N2K minus M1K, well, it will be the difference of all these things. And so it will be something, let me write it. It will be at least, assume N1 different from M1. Then this difference will be the sum, will be larger than N1 minus M1 times something, because in all the differences, no, what I'm saying. No, it's fine. I'm just saying this is larger than this times K times. I just expanded the binomial expansion. I factorized by this, and so I have K terms, which will be Z1 2 power K minus 1. Is it K minus 1? Yeah. Z1 2 power K minus 1. Yeah, you will get N1 2 power 1 times M1K 2 power K plus 1, and so on and so on. It's fine. AN minus BN is equal to A minus B times AN plus 1 plus AN minus 1 plus AN minus 2B plus blah, blah, blah. Okay? So you get this. On the other hand, if you are looking at the difference N2K plus blah, blah, blah plus NTK minus M1K minus M2K minus blah, blah, blah. This is at most 2 to the K, Z1, Z2 to the K, and then plus something which will be a big O indeed, over K of Z3 to the K. And so this is less than K times Z1 to the K minus 1. All those elements, so you don't have many elements, and all of them are less than Z2 to the K because they are taken in N2. So they're less than 2Z2 to the K. Yeah, maybe there is a K or something like that. Well, you check about the, no, not even, because it is the first one and the other one will be, we'll go into that. Okay, so you understand that M1 has to be equal to M1. So N1 is equal to N1. And so on. Then you separate them, and then you show that N2 is equal to M2 in the same way, and then you show that blah, 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 they're all equal. Okay? And so you're in this situation, and this is very efficient because you can build something which is really pretty large here. And that way you get something, the output will be, if you go like that, like capital G of K is big O of K squared. Now, we know better than that. We know better than that, first of all, this big O of K squared is when using veil, with this veil. But for upper bounds, if K is large, Vinogradov has proved better upper bound for the trigonometric sums, where the saving is more polynomial or something like K log K, or K square log K, is more polynomial than exponential. So this was in the 30s, Vinogradov. Okay? And so there have been some works, and I think the most recent one is due to Woolley, and it tells you that G of C. So what Vinogradov was proving that it was a big O of K log K and even less than 3 K log K. And in about almost 100 years, the improvement is that what we know now is that Woolley proved that it is less than K time plus K k log k plus log k plus a constant. And I think the only improvement, recent improvement, is the value of c or something like that. G of k, yeah, sorry. G of k is less than k log k plus log k plus and so on. Well, we expect it is 4k would be a nice bound, which is valid for everybody, and even less, then it depends on the arithmetic. You see, like for powers of 2, you have something bad, like the fact that every integer is the sum of is a congruent to 0, 1 mod 16. This is why you can do better. And if you take a power of 2, you will show that it cannot be, for k is a power of 2, it cannot be better than 4k. Okay. So this is for the Waring's problem. And well, I have 2 minutes left. And I am not going to give the proof. It is a nice proof. It's not too long. It's rather well presented in the book by Vaughan. It is the Roth problem. So I'm a bit out with Waring, and just to say associated questions, and I'll give 1 or 2, and then we'll stop here. Yeah, I think I mentioned already the name of Davenport, who really exploited this this idea of introducing this set W. So in the mid-90s, there was a problem that was circulating among combinatorists. One didn't say combinatorists at that time, it didn't exist, but mathematicians. There were still not just geometers to define all mathematicians, but a lot of people were introduced by that. The question was the following. You take R and L, and you take the integers between 1 and n. You make a disjunct union of R sets of integer. You write it as a disjunct union of I from 1 to R. Then the question was to show that if n is large enough, then at least one of the UI contains an arithmetic progression of length L. Contains an L arithmetic progression. Okay. And this was solved by a young at that time mathematician, van der Waerden. It's not the only thing he did, but it was a surprise because there were a lot of established mathematicians who were working on that, and little guy came with a solution of the problem, which is very delicate. Then it has been generalized in 34, I think Erdős and Turan thought that, by the way, it may be possible even to do it with a set of sequences of integers which are asymptotic density, positive asymptotic upper density. If you have blocks which are already rich enough, then it should be enough to do that. And this was proved by Semeredi. Yes, Semeredi. He got the Abel Prize a few years ago, and is part of the big, one of his big contribution to mathematics, definitely. So it's the first thing was done with proving that there are arithmetic progression of length 3. And this was done by K.F. Roth. I think it is about 43, 44. I think there are 2 papers finally where he got that. And I want to say a word. So this is, I mean, I was mentioning the work of Deshouillers, and this was in 1934. This was conjecture in some way, and this was the case L equal to 3, and this is the general. And by the way, Furstenberg, this was in the beginning of the 70s or 75 or something like that, and there was another proof, which was ergodic proof, which was given by Furstenberg a few years later. Okay, so yeah, there's a full thing to say about that. Then you go into additive combinatorics, and okay, we can speak forever. If I mention in this conferences, I just mentioned one is Roth, because Roth is using the circle method to prove the thing, which may seem curious. So it does the following. I mean, I just give the start. Because of course, you imagine that it has stayed for some time, at least 20 years before being solved. And again, you have a lot of people who are quite interested in this question. And so he's doing the following, he's considering, so he has a set, A, and he considers the element A up to capital N. And of course, you can choose N. N will be large. And you don't have to fix N a priori. You, of course, choose N such that the density is sufficiently large. This is why it is enough to have the upper density and not the density everywhere. It's just using N for which you have enough elements up to N. Not stupid enough to go in a place where there's nothing to say. So, and what he's considering is considering the function f of alpha, which is the trigonometric sum when A belongs to A and A less than N of E of alpha, N, A. Okay, now you have to say something about element in arithmetic progression. How can you count the number of elements, the number of 3 arithmetic progression in the set? 1 or 3 elements in arithmetic progression. Well, of course, if you can write something like A1 plus A2 over 2 is equal to A3. This is not very nice, but there is another equivalent way, which is nicer to write it, is to say A1 plus A2 is equal to 2A3. Now, there is even another way to write it, which is to say A1 plus A2 minus 2A3 is equal to 0. Okay? Oh, but counting that, we know how to do now. We are expert on that. This number of representation is the integral from 0 to 1. I am representing 0, but I'm taking f of alpha squared times f of 2 alpha, of minus 2 alpha. The alpha. So you have a nice integral representation like that. You see, you're just counting the number of 0. So what it tells you that if the property, assume that there is no arithmetic progression, if there are no arithmetic progression, if no 3AP, 2AP, 3AP, 2AP is not interesting, then R is equal to M, to the cardinality. So let us say A of N. N is the number of elements here. This is A of N. Because you have always the trivial solution. There is, of course, the arithmetic progression when A1 and 2, A3 are equal. But this corresponds only to N term. And what is your expectation? And your expectation, even if you say, okay, if I take alpha to be close to 1 over N, as usual, very close to N, I have a contribution. And this contribution is of the order AN square. So this gives you already some point when you have something like that. Now you say, okay, I'm also going to look at around A over K. Well, around A over K, you are in some arithmetic progression. But in some arithmetic progression, you should have also, if there is no If you take the terms in arithmetic progression, if you have no three terms, there should be some difficulty to get some. And so you can say also something around those terms. But of course, you imagine that it is not just trivial and in 1 minute I am going to solve it. But just to say that the idea of the circle method was introduced in that context. Of course, you have to develop it. It's in own direction for solving that. I don't say I could solve that. Oh, still 2 minutes. Something else is that you have also the straight line method. I will tell you how it is a slightly different way of doing things, but this was done by Davenport, and there should be something. Who's doing that? Yes. So it was in the 50s, I think, that Davenport considered the following. Consider the following. You take lambda 1, lambda s, non-zero real numbers. And you assume that the quotient of two of them is irrational, at least. They are not all rationally dependent one to the other, at least letters. And also that they are not all of the same sign. And you can assume without loss of generality, according to what I was saying before, that lambda 1 over lambda 2 is an irrational number, and that lambda 1, lambda 2 is negative. Of course, if two of them are irrational, you can call them lambda 1 and lambda 2. And if the quotient is negative, is fine. And if the quotient is positive, then you take another one which is negative, and it has to be irrational, either with this one or with this one. You add on and you can do that. Okay, fine. And so what we want to say is that if S is large enough, and if you want to follow the thing and try to do it yourself, you can do it with S is larger than, I don't say what it is. K is a number, as usual, an exponent, 2 to the K plus 1. But of course, now we go down to something which is K log K. So there exist integer n, 1, nk, ns, such that lambda 1, n1k plus blah, 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 plus lambda s and sk is less than eta. Eta being given, if you want to say you put 1, it is the same thing about. Okay. So, because it's enough to multiply everything by eta, and the lambda has the same problem. Not difficult. Okay, so now the problem is not the problem to find it is a real problem in some way. So you have your sums, which will be on the line, and you want to see whether you can detect a zero. Well, you can detect something in a small interval. So what you do is to expand this function into Fourier series. So you make this characteristic function, let us say this chi, and so you are counting the number of solutions for which chi is, take the value 1. So you are summing the value of lambda 1, n1, k plus blah, 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 plus lambda s and sk over your set of n1 and k. Okay, and you expand into Fourier series. And here there is a slight problem with Fourier series, of course, that this function is discontinuous. So now you can make approximation. You have one one way, which is I want to know what is an equivalent for the number of solution. You can get equivalent for the number of solution, and then you make some approximation, smooth approximation. You know this function, the word Vala, the name Vala has been mentioned already, so you can find good approximation of that, which are above, which are below, and which will give the same estimates, and you're happy you can do it like that. There's something more brutal. If you just want to show, to answer this, that there exists solution, well, maybe you count them with a different weight. If they are exactly zero, you put a white, which is zero, but otherwise we'll put a smaller weight. So another way would be to do this, to take the green solution, which is to take this function. And since it is continuous, you are more happy with the Fourier expansion. It would converge absolutely, and so you will have, the tail will not be a problem. So you do the same thing. You are counting with this chi tilde. And chi tilde, you know its Fourier transform. It is a sine pi t divided by pi t squared, so the Fourier kernel. And so everything is fine. And again, the situation will be the same on the Fourier side, and the Fourier transform of the real line is the real line. You see, the Fourier transform of Z is R over Z, and this is why you call the circle method. I don't know how you call it, but it is still called the circle method, by the way, but it is a straight line method. We're just now looking on the Fourier side, what is going on. And on the Fourier side, you will have, of course, as usual, a good contribution around zero. And so there will be some major arc around zero. The situation will be even easier. So we said that at infinity, you have a very nice convergence, so everything will be a little low of what you think if you are far enough. And there is some in between, something which is a first major arc. So you don't have too many major arcs. You have a major arc, you have one. Then you have first minor arc, where you are not yet at infinity, and you have some upper bounds. And the upper bounds, by the way, you will have trigonometric sums, even if you're on the real line, it will be periodic. So it will be periodic, but periodic with some oscillating function. But this is not too bad, because on a short interval of length 1, it will be just your trigonometric sum as usual. So you use essentially Weil upper bound. You can use also Hua's lemma. And this is when you use Hua's lemma, then you get this 2k plus 1. We can go. So this is in the first major arc, and then you have something which is absolutely convergent, and you are far away. This is nothing. So this is the way you can prove it, and then improve again similar. So okay, of course, as you know, all these questions are just infinite, and unfortunately, my time is finite, and I don't know how to speak quicker and quicker and quicker, so that I can tell infinitely many things in a finite time. Okay, thank you very much for your attention.
So we thank Professor Deshouillers for this wonderful exposure to the circle method and variance problem, and not telling us too many, infinitely many things. Thank you.
Yeah,
Thank you.
thank you. Again, yeah, let me thank. Yeah, proceed.
Give him the mic.
About the quality of the approximation of the number of representation RSK or RKS.
Yeah.
You had the main term times 1 plus big O of 1 upon n to the delta.
Yeah.
Do we expect delta to 1 minus epsilon to be possible?
1 minus?
Epsilon? Do we expect to be able to save 1 by n in the arrow term?
Ah. Yeah, oh.
Well, if I measure arc,
we expect to save 1 by n.
I don't know. Yeah. No, it is, you are talking about major arc. Yeah, because.
Essentially, that yes, I mean, whatever that Weil says and Hua says.
No, Weil and Hua are meaning on the minor arcs, you can save a lot.
Yeah.
The error term, if you are saving too much on that side, then the error term will come from the major art. So is it on the major art? This is a small constraint. I don't know. I don't know. On the minor arcs, you can save as much as you wish. The beginning is difficult, but the more you take terms, the easier you get.
Thank you, Professor Deshouillers. Like great lectures.
Thanks to
Doing
you.
the synopsis of all the variance problem. And yeah, again, having taken all these efforts, and I do understand that his trip last time to India was not very pleasant. And I was all the time worried whether on the basis of the experience he would accept the invitation. But he has been very nice and he has accepted the invitation and I have come here and given the lecture. Let's give a big applause to him.
Thank you.